Hello, everybody. This is the video for section 6.2 in Calculus 3. So 6.2 is a major section, all right? So it may be one of the most important sections in this chapter and maybe of this entire semester. And the reason is because I will be introducing this new concept called line integrals, right? So what is a line integral? It should probably be called a curve integral because we'll be integrating functions over a curve, all right? But there are two important applications that that are contained in this section, all right? So basically, I'll be talking about three things in this section. And therefore, it's a rather long section, but it is crucial that you understand this concept of line integrals before we go any further. All right, so let's study line integrals. So I have a lot of things already written because I don't want to spend time writing, all the details as I talk on this video. All right, 6.2, the topic is, as I said, line integrals, right? And it should be called curve integrals. But I will be referring to these as line integrals because I can go back and fix some problems in history just because somebody started to call these by a name that should not be used. But anyway, the reason I think curve integrals would be more appropriate is because you are not always integrating over lines. But if you say a curve will certainly include lines. And so, curve integrals as opposed to line integrals. Whatever you call it, we will be integrating over curves. And so we are going to be given a function to integrate and curve over which the function is defined. The outline for this section is threefold. All right. So number one, we will be defining what we mean by the line integral of f over the curve C. And then the differential we use is not dx or dy or even dt, but it's ds. All right. So this is the arc length parameter or arc length differential. And so this is the basic notion of line integrals. All right. And then for many applications, we use rather specific types of functions f. Okay. So for instance, here, this f is a line integral. For this f, f is a real valued function, right? So we are integrating a real valued function over a curve C. Maybe I should be a little more specific, okay? So what kind of a function is this? It is real valued, but it has at least two, sometimes three independent variables. And then we will be integrating this over the curve C. But what kind of a real valued function we are going to be integrating is what we'll be discussing on the second and the third part. All right, so if this f is, remember what the vector field is? The vector field is something you learned in the first section. And then if you dot this with t, okay, so what do you get when you have a dot product? Of course, it is a real valued function, right? So when you replace this f, a real valued function with f dot t, I think I mentioned this before, but f dot t represents the tangential component of the vector field f at each point. And it is a number, it is a real value. If you differentiate or if you integrate f dot t, we get what is called the work integral. Sometimes it's called the flow integral. And if C happens to be a closed loop, then we will call this a circulation integral. All right. And then the third one, we will also be integrating f dot n. So this is the normal component. And when you take the normal component of f, we get something perpendicular to the curve C. And so this will tell you how much of the stuff or fluid or radiation or heat or whatever it is penetrating, going through C from one side to the other. And that function or that integral is called the flux integral. So we will be talking about all three of these in this section. And that's why it is going to be long. And also because we will be talking about line integrals for the first time, it is absolutely essential that you understand how to calculate the calculate line integrals and what those integrals mean. All right, so in general, we'll be given a function, f of xy, okay? So it's real valued. So this is usually defined from R2 to R1, and it's real valued, and a curve, all right, C. And so how do you describe a curve on the plane or in space? Okay, well, the key word is parameterization, right? So parameterize C. And typically, the way we do that, remember, this is from chapter 3, I believe. You write R as x of t and y of t, sometimes and z of t if it's three-dimensional. Okay, but the curve itself is parameterized by one variable, and namely it's t, because its curve itself is locally one-dimensional object. All right, so what does this function look like? All right, and so you can draw a picture like this. Remember, a function f of xy means that I have a real value defined at every single point xy on this plane. Okay, now the curve C is basically a subset of that, right? It's a one-dimensional subset parameterized by this T. So what I drew here in blue is the curve, okay? Going from, let's say, from here, to here. So T, let's say T goes from A to B. And so this is where T of A, well, let's see, that's not T of A. It's R of A is here, and then R of B is the terminal point of this curve, right? Now, over on top of every point of C, the curve, you have a value, okay, which is described by these pillars, okay? So this represents, the height of these pillars, columns represent the value of the function at that point, okay? Now, remember what in Calculus 1, we always go back to Calculus 1 before we attack a new concept on Calculus 3. And so we talked about the very first time when we talked about definite integrals, we had the function f defined on the closed interval AB. And integral of AB over AB of f x dx was defined as, you remember this? What do? Well, you partition A, B into small, smaller, smaller, and smaller subintervals. This is called a partition. And so we find for each, like for, let's say this is the ith subinterval. Then we find the length of the ith subinterval, and then we pick a representative value or x within this subinterval, and then we evaluate the function at that point, which we can call xi star. Okay, xi star is some point in the interval xi, and we evaluate the function at that point, right? So we calculate this, and then we multiply. This is the height of that ith rectangle, and then you multiply this by the length of that subinterval, and of course, this what I just wrote is the area of the ith rectangle, and then you add them all up. Since you have n of these, when you partition this interval into n subintervals, this is called a Riemann sum, as you know. Okay, and the idea is that you take the limit as all of these subintervals become closer and closer to zero in length, and so we say the norm of the partition goes to zero. Okay, and of course the number of intervals, subintervals, will go to infinity. And so if this happens, okay, if this limit exists, we call that limit the definite integral of f over AB. And roughly speaking, if f is non-negative over this area or this interval, we call the integral, which represents the area of the, or I should say area under the function f, right? Okay, in a similar way, if you define for each one, so the first, let's say the first sub arc, in this case it's subcurve or subarc is S1 and S2 and so on. Delta of S1 is the length of the first part of this subcurve, and then delta S2 is the length of the second subcurve, and so on. And then you for each, okay, let's say you pick the ith subcurve, you evaluate the function at some point which belongs to this sub arc or sub curve, right? And so this is xy star yi star, evaluate the function at that point, and that's how tall this arc is, or this column is on top of that point, xi star comma yi star. And we evaluate how tall this is, multiply that by its length. So that is, let's see how can we write this? F of xi star comma yi star. And then we multiply this by the length of that subcurve, which is supposed to be sort of like a straight line because this is, really a fine partition. And then you add all of those things up. So what do you get? It's pretty much the same thing. Basically, take this and throw this and embed that into space where the length, where the interval AB becomes this curve C on the XY plane. At every point, you have a value defined. And so this is more like, the area of the of this column standing on top of the ith sub curve. Okay, and so this is the equivalent of the Riemann sum. It is the Riemann sum over C, and then you take the limit of this as the biggest of all of these. Okay, so I should just say it's the norm of the partition. We use delta for this. This approach is 0. Okay, so in other words, all of these subcurves get tinier and tinier, shorter and shorter, and so you'll have more and more of these. If the limit exists, we call that the line integral. More specifically, or more precisely, should be called the curve integral. But the line integral of f of xy over the curve C, right? And roughly speaking, what is that? It's the area of what you're seeing here in orange, the curtain. Does it look like a curtain? Sort of like a fabric. All these orange things here, they look like sort of a curtain. You can call it curtain or a wall, a curved wall. So if you imagine the wall standing over the curve C, this will be the area of the curve or curtain or curved wall, right? And so that's what this is representing. I hope this is sort of clear. If in the analogy I used before, if you think of all of these as consisting of a bunch of these small, tiny Lego pieces, okay, basically this would be the total number of Lego pieces standing on the curve C, okay? So that's what the line integral represents, line integral. Remember, an integral or integration in general is the continuous version of addition, right? It's a continuous version of sum. And so that's exactly what we're doing. We're just adding up all these Lego pieces that you can find along the points on C. And of course, if you can do that, it is the area of the curtain or the area of this curved wall. Okay, so I hope the interpretation is clear. Now, how do you evaluate it? That's how do you evaluate? Okay. It's not as straightforward as it may appear at the beginning, because the tricky part is this. Let me tell you the tricky part. It's the ds part. Okay, how do you? What is that ds? How do you handle this? Okay, because we have a curve that's parameterized by t. Okay, and we'll find out in just a second. It's actually not too bad. All right, so let's go to this question, and we will be spending the rest of our time today dealing with this question. How do you evaluate a line integral? So I will tell you exactly how to do that. It's not hard, okay? So let me explain. All right, in short, this is what we have. S is the arc length parameter, okay? We have talked about this before. And when we have ds, ds is something we saw. This is the arc length differential, and this is what we have. Whoops, I don't need that extra line here, differential. Okay, so I guess the easiest way to understand this is this. Okay, ds, you can write ds, and ds is, nobody really uses arc length parameter to integrate. We're going to replace this with something. And the easiest way to understand this is you can write ds as ds over dt times dt, right? Because, the differentials like dt will sort of cancel. They behave like fractions. Well, look at this point. Does it remind you of anything? This will be the arc length difference divided by the time, right? Well, that is something we've seen before. That is called a speed, right? And it is the norm of the derivative function r prime of t. Okay, so then you can actually write everything in terms of t. So you can write this way, r prime, the magnitude of r prime dt. You can also write this as the square root of, do you remember this? X prime square plus y prime square, and you take the square root, okay, and that is the speed. Remember that? So that is the only thing you have to insert before dt when you go from ds to dt. All right. Once you understand this part, okay, I think the problem will be rather easy. So let me summarize what I just said, and I am going to use a different color because so that it stands out and it is very clear what you have to know. All right, so our objective right now is to evaluate the integral of f, a two variable function over the curve C on the plane. How do you do that? Well, it's going to be the integral from a to b. This is the first time I'm giving you bounds. Okay, so far this c was just written at the bottom of the integration or integral symbol, and there was no a to b, right? For the first time I'm writing a to b because now we can, and I'll explain what that means. Well, I already did. These are the bounds for t. So you write x in terms of t, y in terms of t. So everything from now on is going to be expressed in t. S will be gone. Instead of ds, I have the speed, which is the magnitude of r prime, and then dt. Okay. As I said before, you can even write this way. It's going to be long, but if you whoops, sorry. If you want to, you can spell out everything about the speed. You know, what is the speed? It is the square root of x prime square plus y prime square. And by the way, if you have a third variable, then it'll be z prime square, right? So this is how you can calculate the line integral. All right, the first, you remember we have three types of integrals in this section. This is the most basic one before we go into the work integral and the flux integral. Okay. And I emphasize this because, you know, sometimes it really helps to understand the overall outline of a section or a lecture before we start, you know, because otherwise you just get confused. We are still in the first section, which is on the line integral, the basic types of line integrals, right? So this is the part that you have to have and you have to discover or you have to calculate before we actually evaluate this integral. Let me give you an example. The very first line integral you're about to see. You must be excited. Okay, so integrate this function. I'll try to make it easier. F of xy is 2x minus 3y squared. Okay, so at 0, 0, the value is 0. Okay, at 1, 2, or you can plug in 1 and 2 and find your answer, right? Over, oh, I forgot to mention here. Here, C is RT, where T is ranges from A to B. So A and B are the endpoints of this parameter T. That's what you're into. That's the numbers you see. Those are the numbers you see there. Okay, so let's integrate this function over C, which is the line segment that you see here from the origin to 1, 2. Okay, so as you go from 0, 0 to 1, 2, this the value, of course, changes, and we are going to integrate this function over this. So what do you have to know? Well, first, let's go ahead and rewrite f not as a function of x and y, but function of t. So, oh, we can't even do that, can we? Sorry about that. There's one more thing I have to do before I get into this. You know what that is? Yeah, it is. I don't have a parameterization yet. So let's go ahead and parameterize C. what would be a good parameterization of C? And by the way, I'm going to do this problem again using a different parameterization to let you see what happens when, because there is no unique way to parameterize a given curve. So I'm going to pick first, because we go from 0, 0 to 1, 2, why not use t, comma, 2t for this? And in this case, I need to go from 0 to 1, right? As t goes from 0 to 1, the points on this parameterized curve goes from 0, 0 to 1, 2. And that's exactly the line segment I need. So that is my parameterization. Let's write f of xy as a function of t. All right, so remember, this is t is my x and 2t is my y coordinates, right? So 2x can be written as 2t. And 3y square, well, y square is 2t quantity square. So this can be written as 2t minus, that's 4t squared, that's 12t squared. Okay, so this is our function f written in terms of t. Now I need one more thing. I need to find the velocity function for this parameterized curve. Because the parameterization is t, comma, 2t, the derivative is 1, 2. Man, that's really easy, right? And so what's the speed? The norm of this magnitude is the square root of 1 squared plus 2 squared, which is the square root of 5. This is something that we have to include in finding my integral. So here we go. What is, let's say, therefore, that's impressive, okay, to have this. This makes you look smart, these three dots. All right, so the integral of f over c is equal to, you ready for this? Integral from 0 to 1, 2t minus 12t squared, that's what you're integrating. And then you have to have that square root of 5. Okay, that's this part here. And then dt. Notice here, I never have to worry about that s, okay? This ds is just really a messy thing to figure out. So you change everything in terms of t, and when you do that, this is sort of a byproduct that we have to include, because in this case, the s is the square root of 5 times dt. The rest is easy. Let's put the square root of 5 in the front. 2t becomes t squared, and 12t squared becomes 4t cubed, right? Just making sure, just so you know, every time I integrate, I mentally differentiate right away just to see my integration is correct. So here, if I differentiate 4t cubed, I get 12t squared. That's exactly what I had before. I am okay then. So then you plug in numbers like 0 and 1 here. It is the square root of 5 times 1 minus 4, and then minus 0. So this is negative 3 square root of 5. This is my answer. Okay, so I hope this is clear. You don't really have to work really hard to do this, but some people just forget to enter that speed. So that is the thing you must remember. And by the way, this expression right now is constant because this is a straight, line segment. This expression could involve t, right? And then things could get maybe a little more complicated. You will have questions like that on your homework. All right, let's remember what I said about this parameterization. It is not unique. So what happens if you decide to do it this way? But if somebody else comes along and say, well, let's parameterize C as R of T is, let's see, I need to go from 0, 0 to 1, 2. So how about if I do 1/2 T, comma, T? Does it take me to the right place? Yeah, as long as you go from 0 to 2. Let t go from 0 to 2, and this starts at 0, 0 and ends at 1, 2. And so that would be the same line, right? Okay, I want you to know something here. Because I changed my x and y, everything I did here will look very different. Well, somewhat different, okay? You're not going to see 2t minus 12t squared. In fact, let's try to figure this out. What is f of xy if this is my x and if this is my y? Remember, my function was 2x minus 3y squared. So it's 2 times x minus 3 times y squared. And this time you get t minus 3t squared. quite different from what we had before here, okay? And then what is r prime? Because remember, I have to have the speed, which means I need to find the velocity, which is 1/2, comma, 1. So the magnitude of the velocity, the speed, is the square root of 1/2 square plus 1 square. That's the square root of 1/4 plus 1. It's the square root of 5 over the square root of 4, but the square root of 4 can be written as 2, right? All right, now we have all the ingredients to throw into the pot to, to, um, to cook up this integral. Sorry, I should say the integral over c of f ds. Okay, so this is the line integral of f over the curve c is equal to the integral from 0 to, remember, this will be 2 because that's my upper limit now with this parameterization. Okay, and now the inside integral is also, integrand is also different. It's t minus 3t squared as opposed to what we had in the first parameterization. And then we have the square root of 5 over 2 dt. All right, compared to the first integral I had, this is very different looking from this. You wouldn't even recognize them as the same integrand, right? But, and maybe it's surprising, maybe it's not surprising. I mean, it could be surprising because, I mean, this looks like a completely different integral, but not so surprising that you get the right same answer because we are integrating the same function over the same curve, right? So let's take the constant out first. So then what t becomes 1/2 t squared, and 3t squared becomes t cubed when you integrate, and then you go from 0 to 2. So this is the square root of 5 over 2, and then you have, what is 1/2 times 2 squared? That's 1/2 times 4, and that's 2. And then 2 cubed is 8, all right? So this will be -6 times the square root of 5 over 2. Of course, you can cancel and simplify this. The answer is -3 over the square, -3 times the square root of 5. This, of course, is the same number as what we got in the first place. All right, so here's the result, or the theorem I want you to know, and it's a very important statement. Let me write it first. All right, so that statement is this: parameterization does not matter. Okay, it does not matter as long as the c, the curve, stays the same. And that is something that you remember. So even if your friend comes up with different parameterization of the same curve, c, your answers will be the same, right? No matter how and who parameterizes the same curve. Now, you can ask this another question. What happens if you go from 0, 0 to 1, 2 in different ways? Okay, so that's a different question, and we'll address that later. But maybe I should say one thing about this. Okay, so so far we went from 0, 0 to 1, 2 this way. Okay, 2 different parameterizations. What happens if you go this way and this way, like 1, to get from here and to like 1, 0, and then from 1, 0 to 1, 2. That's a different curve, right? So this is curve C. This is C1 plus C2 will get you to the right place. But it turns out if you take a different path, okay, different way to get from the beginning to the end, then of course the parameterization changes, but then the integral itself changes. Now that is probably not surprising, right? Because the parameterization doesn't matter as long as C stays the same. But if you change the C, the curve, then of course the integral over C should change. And that is true, okay? However, as we will find out in a couple of sections later, there are some functions, okay, there's very special type of functions for which it doesn't matter how you get from point A to point B, as long as you get from point A to point B, regardless of the way to get there, whether you take the C or C1 plus C2, or however you get from A to B, the integral will stay the same. Okay, and so we will call that kind of f a potential function, and we will study that later. But in general, right now, you should remember, in general, this value of the function depends on the curve c. So if you change that curve c, even if you start and end at the same point as c, the integral will change. Okay, so that's the first part of this lecture on section 2. And now we go into the part 2 of this section, which is on the work integral, work or flow or circulation. So that would be our second point.